record. Okay. So let's see, where are we? Let me stop that. Weekly activities folder. We are in week 7. All right, week 7. Right there. Okay. So let's see what we're doing. Okay. So 4.1 notes is right here, y'all. So today, all we're going to do is just go over 4.1. Okay. My original plan, I was going to do 4.2 as well, but I didn't want to do too much before we worry about the test and stuff like that. Guys, one thing I do want you to notice about the homework for 4.1, look when it's due. 4.1 will be due by 11:59 Wednesday, March 23rd. Okay. So I put it due then, not because it's going to take you a month to get the homework done, but mainly because I don't know how, the review for test 1 has been open for a week or so. And I don't know how much y'all have had a chance to work on the review, but really what I want you guys focusing on at this point is the review for the test, not really anything else. I mean, that's my main concern is, excuse me, I really want you guys to focus on the review. So that's why I made the homework due March 23rd. Guys, that is not the Monday that we come back. That's the Wednesday of the week we come back. Okay, so the question is, do I have homework over spring break? Well, maybe. If you knock it out beforehand, great. But if you don't, then you'll have a little bit of homework over spring break. But again, it's not due the day we come back. It's due the Wednesday we come back. Okay, so you got some time. And then Wednesday, this Wednesday, all we're going to do is answer questions from the review. Okay. So when you click here, you get the 4.1 notes. Let me get my OneNote. It'll open up this Wednesday. Yeah, it's going to open up this Wednesday. Okay.
And then next week, what?
So next week, let me come back over here so you can see again. So remember, this Wednesday, all we're doing is review, right? Take a look right here. Next Monday, we have what? No class. That's me giving you the day to take the test. Okay? And then we'll come back on Wednesday the 9th. You know what I mean? So we're going to be here both days this week. Next Monday, a week from today is the day that you have off. Yeah, the quiz is due. Yeah. So make sure you guys take the quiz because I did open it up this past Wednesday. Okay? 10 questions, guys, right? Nothing too out of the ordinary. Yeah, next Wednesday we'll probably do 4.2 and 4.3. They're kind of short sections. So we'll do both of them that day. Okay, yeah, make sure you get your quiz done, guys. Remember, the quiz is due on Wednesday, okay? This Wednesday will be the 3rd. Okay.
Oh, yeah.
Or the 2nd. This Wednesday is the 2nd, I'm sorry.
No, I sometimes forget that there's only 20 days February. I was like, wait, how is it? It'll be the 2nd or 3rd.
Yeah, because today's the end of the month, right?
Yeah.
Okay, so let me see. Let me bring this down here. Bring this down here. Wow, we did a lot of work that day. Oh, that was the logarithmic stuff. Okay, here we go. So, here we go. So, y'all, 4.1 talks about, here we go. Yeah, talks about related rates. Okay, so just to give you a heads up, y'all, so far what we've done, especially in chapter 2 is all about limits, right? We're taking limits from the left, limits from the right. We looked at graphs, but we're really talking about limits in chapter 2. In chapter 3, we started talking about derivatives. We really haven't done any kind of word problems per se. We might say can we find the equation of the tangent line, stuff like that, but we really haven't had any word problems. Chapter 4 is about the applications, or at least part of chapter 4 is about applications of derivatives, okay? So 4.1 is related rates. This is the first section, y'all, where we actually do some word problems. We're actually doing some applications of derivatives here, okay?
So the math is what we've already done, but we're trying to.
Apply it now.
Okay.
Yeah, now we're going to talk about how to apply it, right? Because is it important for us to know how to do derivatives? Yeah, it is. But then if we can't apply it to anything, well, then what's the point of actually, you know what I mean? Like we know we can find the derivative, but we got to figure out where can we use it, okay? So look, y'all, 4.1, the objectives, number one, we're going to express changing quantities in terms of derivatives. We're going to find relationships among derivatives in a given problem, and we're going to use the chain rule. Okay, so guys, one thing I really want to emphasize, and again, before I come to class, I go through all these problems myself. In every one of the problems, we are going to use the chain rule. Okay, we're going to use the chain rule in every single one of these problems, all right? So there is a strategy on how to do related rates problems. So it says assign symbols, to all variables involved in the problem. Draw a picture if we can. State in terms of the variable the information that's given and the rate to be determined. Find an equation relating the variables introduced in step 1. Step number 4 says we're going to use the chain rule to differentiate both sides of the equation. Found in step 3. And substitute all known values into the equation from step 4. Okay, so here's our first problem. The first problem here says, let A be the area of a circle with radius r. If dr dt equals 4, find dA dt when r equals 1. Okay, so the first thing I want to think about here, y'all, in this problem is, do we know a formula for the area of a circle? Anybody remember the formula for the area of a circle?
Pi times diameter?
Almost. The area, y'all, is pi r squared.
Oh, pi.
Yeah, close, right?
No, that's as close as I did.
Pi d would be the circumference, right?
Yeah.
And remember what the circumference is? It's like walking around it. Area is the middle, is the stuff inside, right?
I remember.
Good. Okay. I want you to notice what we're trying to find. We are trying to find dA dt. So what this means is we are taking the derivative of our function. Oops. You're glad I don't teach English? I misspelled a word. Derivative with respect to t. Okay. So we're looking for the derivative of a. We're looking for the change in the area with respect to t. Okay. No, it would be a prime, but again, it's with respect to t, right? So one of the issues, Don, when we use like the prime notation, is that it doesn't really tell us what we're taking the derivative with respect to what variable. Okay. So the other thing is they gave us an important piece of information. They said that the dr dt is equal to 4. Okay, so we're going to take the derivative of a with respect to t. So the derivative of a with respect to t is dA dt. Okay. Now we got to take the derivative of this part. What's going to happen with that exponent of a 2? Comes down to the front. We still have the pi, right? Now we only have an r to the first power. Now we still have to take the derivative of r. So we call that dr dt because we are taking the derivative with respect to t. So guys, one thing I wanted to mention is that, and I told you this at the beginning of class, we use the chain rule a lot. The chain rule is being used here because we're taking the derivative with respect to time. We don't know what r is equal to. You know, r might change based on the time. The radius of the circle may change over time. So we call it dr dt.
So that's the derivative of r plus pi. That's our derivative of r times pi, and then we subtract the derivative of pi.
No subtracting here, right? I'm not subtracting anything. Look what we're doing. So think about it this way, Don. R is a function of t. Okay, so the radius changes based on the time. So when I'm taking the derivative of this, it's just like I was taking the derivative like I normally would. Bring down the 2, leave the pi there, take 1 less of my power, but then now I have to take the derivative of my r function, and we call that dr dt.
That's not the chain rule where F in C, derivative of C minus derivative of F, D. What's that?
The quotient rule, where I do the bottom and the derivative of the top, you talking about that?
Yeah.
That's the only time I do a subtraction.
Maybe it's a different.
Yeah, there's no subtracting here at all. Okay, now take a look, y'all. We're going to keep moving along here. So dA dt equals 2 pi. Now, did they give us a value for r? R is 1, right? Did they give us a value of dr dt? Okay, so now we're going to go straight across. 2 times pi times 1 times 4. Anyone know? Well, hold on. Don't make it hard. What's 2 times 1 times 4? There's your answer. 8 pi, right? Now, guys, obviously, when you're doing this on My Open Math, you're going to do 8 times 3.14 and change whatever, and then you'll find your decimal approximation, right? So I'll get my calculator going here. 8 times pi, and I'm coming up with 25.1327. There you go. Okay. Okay, so again, what I'm trying to do here, y'all, is have an understanding that I'm going to be using my chain rule throughout these problems, okay? So look, let me scroll over to the next one. We're going to do it the same way. Okay, so look at this problem. It says the area of a healing wound is given by A equals pi r squared. So we have a wound, I don't know, we got shot or something like that, right? Right? We got a wound somehow, right? Yeah, well, just, I know, but it has to be perfectly circular, John. I'm just teasing you. I'm just teasing you, buddy. I'm just teasing you. Okay, look what it tells me. Huh? There you go. We got hit by a paintball. Okay, we got hit by a paintball. So we got a massive bruise, right? It's all infected. I'm just kidding. Okay, take a look here. It says the radius is decreasing at a rate of 3 millimeters per day. Okay, I want you to notice something here, y'all. When it's talking about the rate, that's telling me in the rate of the radius, that's my dr dt, because the change of the radius, right? The change of the radius is decreasing at a rate of 3 millimeters per day. So guys, question, if it's, I'm sorry? That would be like my slope, right? But because the radius is decreasing, would it be a positive or a negative number? Negative 3 millimeters per day. Okay, at the moment when r equals 36, how fast is the area decreasing at that moment? Okay, first thing we're going to do, we're going to write down our formula again, right? This is the formula, A equals pi r squared. We obviously have a circular wound here, right? Because they're giving us the formula for the area of a circle. I'm sorry? Okay, look what it's asking me. How fast is the area decreasing at the moment? When it's asking me how fast, it's asking me to find dA, that's right, dt. It's asking me to find the rate of change of the area with respect to time. We're going to do this just like we did the previous problem. What was the derivative of pi r squared? 2 pi r. One other thing. What do we need? There you go. That's the chain rule part, y'all. Okay, so remember, if I was taking the derivative with respect to r, it would have just been 2 pi r. But because the radius is changing with respect to time, I have to bring in that additional factor of dr dt. Okay, now we're going to keep working here. dA dt is equal to 2 pi. Do we have a value for r? The radius is 36. Guys, I know they didn't give me a units here, but it's supposed to be 36 millimeters because that's the units that we're using right there as well, okay? Did they give us a value of DRDT?
Negative 3 millimeters.
There you go. Negative 3 millimeters per day. Remember, the radius is already in millimeters. Okay. So yeah. So we're good. We don't got to worry about anything else. All we're going to do now, y'all, is we're going to multiply straight across. And guys, I'm going to use my calculator for this. I'm just going to multiply, you know what I mean, straight across. Okay, so I'm going to go 2 times pi times 36 times, what is that, a negative 3? Okay, and I'm coming up with a negative 678.5840. Okay, so negative 678. And again, the only reason I'm writing it this way, when you guys are entering your answers in MyOpenMath, is there a pi symbol there?
Yeah.
There is? Okay. Okay, I wasn't certain, y'all. 5840. So you could do this, or you could say, I'm sorry, John, what was it? Negative 216? Pi. Okay, that's what we came up with. Now, I want to point something out here, y'all. We're pretty much done with the problem, right? Either one of those is the same thing. This is the decimal approximation. That would be like our exact value, right? And this would be millimeters, or millimeters squared, I should say, per day, right? Yeah, look right here. Oops. Whoa. That's right. There we go. This right here, y'all, was millimeters. So when I take millimeters times millimeters again, we get millimeters squared per day, right? Because area is always in square units, and it's changing per unit of time. In this case, the time was per day. Now, I want to, I'm sorry? Well, I mean, if you had a circular, if the wound was perfectly circular, yeah, this is how we would do it, right? So guys, the one thing I want to mention though, look at the question. So the question says, how fast is the area decreasing at the moment? When you enter this into MyOpenMath, you're going to enter in one of two values. You're either going to enter 678.5840 millimeters squared per day, or you're going to enter in 216 pi millimeters squared per day. Does anybody know why I dropped the negative sign?
Because I know
No. Look at the question. What word am I underlining here? Decreasing. Decreasing already implies that it's what? That it's negative. Okay. So the reason I'm mentioning that, y'all, is when you're doing your homework, if you're entering in the negative value and it's gonna say like, oh, it's not right, and then after somebody tries, does it give you what the right answer is? It does. Okay, and then if it comes up as positive, you might be saying, oh, like why is it positive? Because the way the question is worded. If the question would have said, how fast is the area changing at the moment, then we would use the negative, because it's changing in a negative direction because the area is getting smaller. But the fact that they word it as how fast is the area decreasing at the moment, then the negative is already implied because it's telling me that the area is getting what? Smaller, right? So just to give you a heads up, and that's just, and it's not that, you know, if you get the problem wrong, guys, don't fret about it. It's just the wording behind it. You know what I mean? And those are, unfortunately, in math, those are things that are in the problem that, you know, we understand the concept. I just didn't read it correctly or whatever it happened to be. You understand my point? John? Well, acceleration due to gravity is negative, right? Because you're coming down to the negative 9.8 meters squared per second is the acceleration due to gravity, but it's negative. It is negative. Yeah. There you go. Okay. That's okay. That's okay. Trust me, I haven't done physics since the 90s, man. So you're good. Don't worry about it. All right, let's take a look at the next one here. It says a spherical snowball is melting in such a way that the radius is decreasing at a rate of 0.2 centimeters per minute. At what rate is the volume of the snowball decreasing when the radius is 18 centimeters? Look what the direction says. Note that the answer is a positive number. Okay, why do they tell me the answer is a positive number? Because it's going to be decreasing. That's why we're going to put a positive number. Okay, again, it's just the way the problem is worded. But if the question would have said, at what rate is the volume of the snowball changing, then we would include the negative into it. Okay. So hold on. Let's hold on. Let's do one piece at a time, and then I'll get to your question. Okay. Look at the first part, guys. A spherical snowball is melting in such a way that the radius is decreasing at a rate of 0.2 centimeters per minute. Does everybody agree that that's telling me that dRdt is a negative 0.2 centimeters per minute? That's the value of dRdt? That's right. And I want you to look what it says right here, John, and I underlined it for us. The radius is decreasing. That's telling me the change of the radius. And the change of the radius is happening based on the time. It's decreasing at a rate of 0.2 centimeters per minute. Every minute, the radius of this sphere gets smaller by 0.2 centimeters for every minute that passes, right? That's why my dRdt is negative. Now the question says, at what rate is the volume of the snowball decreasing? So what we're trying to figure out is, what is dV? dt. That's what we're trying to figure out. What is the change in the volume? So look, y'all, they were nice enough to give us the formula for the radius of the sphere. Here's the formula, right? I just copied it down again. A volume of the sphere, I'm sorry. What did I say? Radius of the sphere. Yeah, that doesn't make any sense. Sorry, yeah, for the volume of the sphere. Okay, so we're going to take the derivative of v with respect to t. We're taking the derivative with respect to time. Okay, first question. What am I going to do with this 3? Move it to the front. Can I think of that 3, y'all, as 3 over 1? Okay. And then aren't we going to leave the 4 over 3 and the pi where it is? And then what is the derivative of r to the third? Wouldn't it be r to the second? I need one more thing. dr dt, right? Because we're taking the derivative with respect to pi. Okay. So, as we continue along here, y'all agree with me that that 3 and that 3 are going to go away? Okay. We have a 4 pi r squared dr dt. And now we can go ahead and plug in our value. Did they give us a value for the radius? 18 centimeters, right? We knew the radius is 18 centimeters, it told us right there, and we had our value of dr dt. So we're going to write 4 pi times 18 squared times a negative 0.2 centimeters per minute. And y'all, I'm going to go ahead and I'm going to do units here just so we understand what's happening. Remember, this is 18 centimeters squared, and that's a negative 0.2 centimeters per minute. Okay, so I got to figure out what 18 squared is. 324 times 4 times negative 0.2. I'm coming up with a negative 259.2 pi centimeters cubed per minute. I want us to understand why it's centimeters cubed. When we're squaring 18, not only are we squaring the number 18, we're also squaring the units. So centimeters squared becomes centimeters squared. With another centimeters gives me cubic centimeters, okay? And then, y'all, if I'm doing this, if I'm going to find like a decimal approximation, I'm going to take that value and I'm going to multiply it, what, by pi? And I'm coming up with a negative 814.3008. The negative 814.3008. Again, this is still cubic centimeters per minute, right? And then when I look at the directions, and I want y'all to know something up here, y'all. See how they already gave me the units? Do you see how they were already cubic centimeters, so centimeters to the third over the time? So I didn't have to worry about plugging in the units on this particular problem. But remember what it said, note the answer is a positive value. So here I would just write in 814.3008, right? And there's my answer. Again, why? Because it's already telling me that it's decreasing. Does that make sense? We're good, John? Guys, those of you who are watching from home, are we good so far? Julio, Linda, Noel, are we doing okay?
Yes, sir. Everything good.
Okay, just checking with you. All right, thank you, Julio. Just wanted to make sure you guys are okay with this. Okay, so guys, again, do you understand that I'm using the chain rule every time because I'm having to introduce that DRDT, or like in the last three problems, I'm having to bring in that extra factor? Okay, just wanted to double check with you guys. All right, let's try another one that we got here. Let me zoom in so we can kind of see what's going on. Okay. All right, it says, let's see, gravel is being dumped from a conveyor belt at a rate of 20 cubic feet per minute. It forms a pile in the shape of a right circular cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 18 feet high? Okay, recall that the volume of a right circular cone with respect to height h and radius of the base r is given by, okay, so they've given me a formula here. Let's see if we can figure out what's going on. So we have gravel, and gravel is forming at a rate. Okay? So we have something like this, right? And gravel is falling on this thing, and it's falling in the shape of a right circular cone. Now, I'm sorry? No, no, I don't know, John. I don't know. Sorry, I don't know. All right, so let's take a look here. I want you to look at the first part. Look at the first sentence. It's being dumped from a conveyor belt at a rate of 20 cubic feet per minute. Okay, so we have our formula, y'all. Our formula is V equals 1/3 pi r squared times h, right? Okay, and the other thing is, since we're talking about the rate, and the rate is coming at 20 cubic feet per minute, does everybody agree that that value happens to be the rate of the volume? And the way I know it's the rate of the volume, y'all, is it's 20 cubic feet per minute. Cubic feet is anything that's in terms of cubic units is telling me, hey, that has to be volume, okay? So they're giving me that piece right there. They're telling me that that dVdt is 20 cubic feet per minute, okay? And then the other thing it tells me is the diameter and the height are always equal. So if we have a circle that looks like this, there's the diameter and the height. The diameter and the height are going to be the same value, okay? All right, let's see. How fast is the height of the pile increasing when the pile is 18 feet high? Look what they're asking me to find. How fast is the height of the pile increasing? We are looking for, y'all, the HDT. That's what we're trying to find. Okay? So first thing we're going to do, we're going to write down our formula. Okay, and now we're going to start taking the derivative with respect to time. Okay, so when we take the derivative with respect to time, we come up with dv dt equals 1/3 pi. Okay, now, y'all, when I'm taking the derivative of this, I'm going to have to think about using my product rule. I have two different functions here. I have an r squared, and I also have an h. So I have to use my product rule here, okay? So look, the product rule says we're going to write the first function, r squared, times the derivative of the second function. Well, the derivative of h would just be dh dt. Okay? Plus the second function, which is h, times the derivative of the first function. The derivative of r squared, y'all, would be a 2r and then a dr dt. Okay?
So wait, what is that first and second?
Using the product rule, because I have,
What I'm trying to say is that there's a derivative times the, plus,
so it's the first function times the derivative of the second, plus the second function times the derivative of the first.
yeah, that's what I was thinking of, but I confused it with that.
Okay?
But I like that way.
So look, I'm going to keep working through here. 1/3 pi. Okay. Now, with a couple of things we already know, guys. It told me from the original problem, it told us that the height of the pile was how much? 18 feet, right? So we know the height is 18 feet. Everybody agree that the diameter is also 18 feet? Because didn't it tell me that the diameter and the height were always equal? So if the height was 18 feet, y'all agree the diameter is also 18 feet? Anybody know what would the radius happen to be? Okay, how much is half of 18? 9. Okay, so I'm sorry, why what? Because isn't the diameter the distance from here to the radius is that distance where the diameter is the whole thing? Better? Good, good. Okay, so look, y'all, we're going to start plugging in some values. We know that the radius is 9, and we know that the height is 18. So the radius right here, I'm going to put a 9, so that's going to be a 9 squared times whatever dh dt is, that's what I'm trying to find, plus the height we already said was 18, right? Times 2 times the radius, which was 9, times dr dt. Okay? You know what I know? We'll come back. Didn't we have a value for dv dt? Wasn't that equal to 20 cubic feet per minute? Okay. So this is 20 cubic feet per minute is equal to, guys, instead of writing 1/3 pi, I'm just going to write it as pi over 3. All right. 9 squared. Everybody agree 9 squared is 81? Okay. Let me see. Let me take my calculator. I want to figure out what 18 times 2 times 9 is. 18 times 2 times 9 is 324? dr dt. Okay. Now, I want to mention something here, y'all. Just so that I don't forget what it is I'm trying to find. Look, I put it right here at the beginning. We're looking for dh dt, right? Okay. So, one thing I want to mention, y'all, is in the problem, let me clean some of this mess up here. In the problem, do you see how they told me the base height and the base diameter and the height were always equal? So we knew that the diameter was equal to the height, right? We knew that from the get-go. Isn't the diameter the same thing as twice the radius? Because the radius is half. So if I multiply the radius by 2, I get the diameter? Okay. And let's think about it this way. If I were to take the derivative on both sides of this little equation that I have right here, you guys, if I were to take the derivative on both sides, would you all agree with me that this would be a 2 dr dt equals a dh dt? If I took the derivative on both sides with respect to t? And then one last piece I want to mention. If I were to solve this equation right here for dr dt, would you agree with me that dr dt would be half of dh dt? Just by dividing both sides by 2? I'm just getting rid of the 2 by dividing it on both sides or multiplying by a half. Okay. The reason why I'm bringing that up, y'all, I'm trying to solve for dh dt. But I have both variables. But now that we know that dr dt is half of dh dt, we can replace this with a 1/2 dh dt. Is that, did I lose you guys there? Well, if remember, John, if I'm taking the derivative with respect to x, I'm not taking the derivative with respect to x. I'm taking the derivative with respect to t here, right?
No, okay, it's like how I like to treat R with the equation. So, because
That is the equation, right?
I mean, I'm kind of writing, when I look at this, how many days algebra, that is how I just do it when I write dr versus t.
Uh-huh.
Equals d over dt. So, or what is that?
Okay, so look, let me explain it to you. Take a look. Do you agree that it told us that the diameter was the same thing as the height? Okay. Isn't the diameter the same thing as twice the radius? Okay. All I did from going from here to here, as I said, look, let me take the derivative with respect to t. So the derivative of 2r would have just been a 2 dr dt, right? Okay.
Trying to say, how can I write 2r equal to inside of that bracket? Because I want to find the derivative of inside.
Okay, so you're asking why am I like, how do I know I'm going to end up taking the derivative?
How do I represent it? How do I write as if I was just trying to, like, how would I say, so since you're not finding yet, right? Do I just write, that's sort of,
Okay, yes. So yeah, think about it this way: the diameter and the height. If it makes it any easier, Don, do it like this: the diameter and the height are functions of t. Does that make more sense?
yeah. I get it. I'm just trying to find a way to write this down as a representation. Because I'm doing one long horizontal thing. So it's very vertical, with deep, width, and this equals this, and trying to write, now that the derivative of this equation equals 2 dr which is d. I was just trying to find out how to write the derivative.
I'm not certain I'm understanding what you're asking me to do.
That's
Okay, it's okay. It's okay. Just wanted to make sure that we're good here. So dr dt was half of dh dt. Now again, guys, I want to bring something up. The reason why I was doing that, remember what we're trying to solve here? We're trying to find dh dt. On this side of the equal sign, I had two different variables. I had dh dt and I had dr dt. So I need to write them in terms of the same variable. I needed them for both of them to be dh dt. Okay. So look, now I have 20 cubic feet per minute equals pi over 3. This is 81 dh dt. I need to figure out what half of 324 is. 162, DHDP, right? Okay, we can go ahead and combine these together because they are the same, they're still DHDPs. So I'm kind of running out of room, y'all, so I'm going to do this over here on the side. So I'm going to say that I got 20 cubic feet per minute is equal to pi over 3. And I'm adding the numbers 81 and 162. What is that, 243? Okay. 243 DH and DT. Okay. Are we good?
Yeah.
We're good? Okay. All right, question, y'all. How would I get rid of this pi over 3? Reciprocal, right? 3 over pi? 3 over pi. So now I have a 60 over pi cubic feet per minute equals a 243 dH and dt. And then do you agree one more time we would do the reciprocal 1 over 243 on both sides? So that that one and that one would cancel. So I now have a 60 cubic feet per minute over a 243 pi equals dH dt. And now all we're going to do, y'all, is just take our calculators and figure out what this value is going to be. Okay. So 60 divided by, let's see, 243 with a pi. And I'm coming up with pretty small numbers here. DH is 0.78, or let's say 6, 0.786, or 786, I'm sorry. Yeah, 0.0786, right? There we go. And there's my DHDT. Yes, give me 1 second. 0.0786. Okay, so it's back to this step. And I added 81 to it. Because aren't these guys right here like terms now? Aren't they both DHDT? Right? So all I did is say 81 and 162 was 243. And then we went from there. Okay, let me ask you a question. Was this problem harder or easier than the ones we did before? Harder, right? A couple of things that made it harder, y'all. A couple of things that made it harder. We had already done the volume problem. But what made this problem more difficult was we had some relationships that were there. It told me like the diameter and the height were the same. And if the diameter and the height are the same, then that means that the height is half the radius, right? Or the radius is twice the height. And then because we're trying to find DHDT, we had to use the product rule because we had two functions, right? One of them is the height function, one's the radius function. And then we had to do that substitution. So we had to do multiple steps in this problem, okay? We definitely had to do multiple steps in the problem. And yeah, it definitely made it much more challenging to do. Okay? Alrighty. So let's take a look at the next one here, y'all. Again, we'll go through it in pieces, one piece at a time, just to make sure we understand what's going on here. And so this problem is kind of like the one we did before, right? Look, instead of gravel, now we got sand. Same kind of thing, right? Sand is pouring out of a pipe and is forming a conical pile on the ground. The radius of the pile is increasing at a rate of 5 meters per hour. Okay, so I'm gonna put something here, y'all. This sentence right here is telling me that dRdt is increasing at a rate of 5 meters per hour. Okay, when it talks about a rate, that's always telling me a derivative. Okay, the derivative is always, so like John mentioned earlier, the derivative tells you the slope. Yeah, it does. Tells you the slope of the tangent line. Remember what the slope is? It's the rate of change, right? Like the rise over the run, that kind of thing. So anytime I see the term a rate is changing, that's telling me a derivative. Okay. Look, the other thing it tells us. It tells us that the height is always 1/2 the radius. So the height is 1/2 the value of r. Okay. Now, let's see if we can figure out part A. Part A says, when the pile has a radius of 13 meters, what's the volume? Okay, so look, they give me a formula for the volume. It's 1/3 pi r squared times h, right? That's the formula that they give. Okay, now we're going to do a little plug and chug here. So we're going to say, because we're just trying to find the volume, we're not finding any rates. This next step, y'all, is just a direct substitution. V equals 1/3 pi. Let's see, the radius is how much in this case? 13? Okay. Isn't the height the same thing as half the radius? So I'm going to put 1/2 times 13. Okay. So look, y'all, a 1/3 and a 1/2 is really a 1/6. Pi, a 13 squared and another 13 is really a 13 cubed, isn't it? I'm just going to use my calculator now to figure out what my answer is. Okay, so let's figure out what's 13 to the third. Yeah, to give me 1/6, right? Okay, so I came up with 2160, 2197. I'm doing this on my calculator also. Everything is going to be like decimal stuff times pi, and then I don't know, divided by 6 because we got a 6 on the bottom, and I'm coming up with like 1150.3465. 1150.3465. Okay, so 1150.3465. Yes. Okay, and it is in cubic meters already, right? Notice, I didn't really have to do a whole lot of anything here, right? I was just able to kind of take those numbers, plug them in. The part A was really an algebra problem, right? We didn't have to do any derivatives or any function stuff like that. Decimals is going to be fine. Okay, and again, I'm just trying to, like, I'm going to 4 decimal places. I always figure 4 is, better than 1, right? At least have a few on there. I think when I was doing these problems and I was checking the answers, they were accepting 2, or like when they were giving me the answer, they were giving me the 2 decimal places. I'm always just doing 4, but you do more, it's not going to count as wrong. You know what I mean? Okay, so now look at the second part, part B. It says, what is the rate and change of volume? Okay, so look, I'm going to use this formula that we have here. So the formula we had is volume equals 1/3 pi r squared times h. Before I do anything different, I'm going to do some substitution. We knew that the height was half the radius, right? Because it told me that from step 1. If I do that here, do you all agree with me that I would end up with a 1/6 pi r to the third? So 1/3 and 1/2, 1/6, r squared and another r would be 1 to the third. Before I go on, are we good on how we got to where we are? I'm gonna do that step in a second. Okay. Right now, and actually, look, I mentioned earlier that I was going to 4 decimal places. The directions here actually tell me to go to 2. Okay, so we could do 2. Right? We could say this would be what 1150.35. Okay, so it is telling me to go to 2. Okay, I didn't even catch that earlier. All right, guys, before I go on, are we good on how we got to this step right here? Matias, am I doing okay? Yeah, are you sure? Everybody, you're good? Thumbs up all the way across? Okay, just checking with you. All right, remember what we're trying to find? We're trying to find the rate of change of the volume. So we are looking for now, y'all, dV/dt, okay? The derivative of the volume, right? What am I going to do with that 3? Move it to the front. I got a 1/6 and a pi, okay? What's going to happen to my R now? R what? Remember, we brought the 3 down, right? R squared, good. Okay, one extra part, y'all. Y'all remember what we're going to add? What's my next factor? We got one extra piece. Chain rule, dRdt, good. Very good, you guys. That's awesome. To me, the hardest thing, y'all, the hardest thing about calculus 1 is just remembering that chain rule, that additional factor is always going to be in there. The reason being, and you know what, like John brought up a point earlier, and I don't know if I was necessarily understanding him or not, but one thing I really want to emphasize, y'all, like the functions they're based on the time. And so when we're taking the derivative, that's why we got to bring in that dRdt, because R is a function of time. The radius changes based on the time. How does it change? I don't know. I don't have we don't have an equation for that function, but it is based on the time. That's all we always have to bring in that dRdt. Okay. Okay, let's continue here. So we're going to go dV/dt equals 3 and 6 will reduce. That's a 1/2 pi. Didn't it give me a value for the radius earlier? The radius was how much? 13. So that's going to be a 13 squared. And didn't we have a value for dRdt at the very beginning? There we go. 5 meters per hour? Okay. Again, y'all, the radius was 13 meters, okay? So look, we're going to go really slow here. This is going to be a 1/2 pi. And then I'm going to take 13 and square it. I know that's 169 times a 5. That's an 845. 845 meters cubed per hour. Very good, John. And it's really something like dV/dt is 845 pi over 2 meters cubed per hour. But I'm still going to end up using my calculator, aren't I? Because it is asking me to write my answer using 2 decimal places. So I got to take 845 times pi, and I got to divide it by 2. And so to 2 decimal places, y'all, I'm coming up with 1327.32, right? So 1327.32. And that's what we're going to enter in right up here at the top, 1327.32. And the units are already written there for us, so we don't have to worry so much about units in this case because they've already written. Let me ask you a question. Was this problem harder or easier than the other one we did? A little bit easier. I didn't have to use the product rule here, right? Because we were able to make that direct substitution from the very get-go with the height being half the radius. Yeah. Okay, good, y'all. I'm really glad that you guys caught on that that's always that additional factor that I got to bring in using that chain rule, right? I got to use that DRG2. Okay, here we go. We got another problem. Okay, so this one here, y'all, says a rotating light is located 18 feet from a wall. Okay, so look, I already got a little bit of a picture here. Y'all agree with me that this value here is 18 feet, right? So there's my rotating light located 18 feet from a wall. The light completes one rotation every 4 seconds. Okay, so it's a rotating light. So it's kind of like those lights that you see at the airport, right? That are doing that number. It's a rotation. So it makes one rotation every 4 seconds. Okay, let me ask you all a question. When we make a complete rotation like that, what is that value? You know, when we go around 360 degrees or in radians? 2 pi. Okay, so one rotation is equal to 2 pi, right? Man, aren't you glad we were in pre-cal last semester? I know I am. Okay, one rotation every what? Every 4 seconds. Okay, so look, y'all, we're going to do something here. We're going to call that angle theta. Okay, that's usually the term we use right when we do angles. So we're going to say that d theta dt is equal to 2 pi radians every how many seconds? Every 4 seconds. Wouldn't that actually be pi over 2 radians per second? You just reduced it? Okay. So I've only read the first 2 sentences. I'm going to keep reading here. It says, find the rate at which the light projected on the wall is moving along the wall when the angle is 20 degrees from perpendicular to the wall. Okay, so look, let's call this value here, let's call it B. Okay, I don't know, I'm just picking a letter, B, W, whatever you want to say. I'll use W for the wall. Okay. We're trying to figure out how fast is that light moving as I go across. Okay, let me ask you all a question. I don't know if you remember this from Trig or not. If you don't, that's okay. I'm going to pull something up real quick here. Let me come back this way. Let me scroll up to the top. Okay, formula sheets, chapter notes, right? I gave you all this stuff in the very beginning of the semester. Let me see. Trig identities. I think it would be probably here. If I have it, it's going to be here. And I don't even know if it's in this part or not, but it could be. Okay, let me see. Yeah, that's what I was trying to find. I don't even think it's in this part here. Yeah, this is, I don't think this one has it, but no, I don't really have it here. Okay. But John seems to remember. Okay, so John, what is the trig function that correlates the opposite side to the adjacent side? Tangent. Very good. So look, y'all, tangent of theta would be equal to W over, in our case, 18. Okay. All right. What we're looking for, we're trying to find the rate at which the light projected on the wall is moving when the angle is 20 degrees perpendicular to the wall. What we're really trying to find here, y'all, is dW dt. That's what it is we're trying to find. We're trying to find the rate at which that value is moving. Okay? So this is what we're going to do. We're going to use the chain rule here. We're going to take the derivative with respect to t on both sides of this equation. Okay, anybody remember what the derivative of a tangent was? Very good, secant squared, right? Okay, so we're taking the derivative on both sides, y'all, with respect to t. So the derivative of tangent would be secant squared theta. Remember, I'm using my chain rule. So I still have to take the derivative of my angle. That's what we call d theta dt. Okay? On the right side, I'm taking the derivative on both sides. I have a 1 over 18. Remember, I can think of that w over 18 as 1 over 18. The derivative of w, you guys, is what we call dw dt. What we're trying to do, we're trying to solve for that guy right there. We're trying to find dw dt. Okay, there's another couple of pieces of information that we have. It tells me that the angle is 20 degrees. Isn't that telling me that theta is 20 degrees? Okay, so look, what we're going to do is right here, we're going to write secant squared of 20 degrees. I'm going to leave a little degree symbol right there, y'all. Okay, 20 degrees times d theta dt. Didn't we find what d theta dt was? Wasn't that equal to pi over 2 radians per second? Pi over 2. I'm sorry? Remember, radians are real numbers, right? So we don't necessarily need to do any conversions because when we find secant squared, it's just going to be a real number value as well. Okay? Equals 1 over 18 dw dt. Y'all agree that we can multiply everything by 18 to get rid of this fraction down here? So now I have 18 secant squared (20 degrees) times pi over 2 equals dw dt. Okay, so y'all, I know John has mentioned this before. John, you have an Inspire calculator, right? Okay, so I don't know what kind of calculator. What yours is TI something? 83 plus. Anybody else have a calculator with them? What kind do you have? Is it TI? Is that Casio? Okay, yours is Casio. So guys, I don't know what kind of calculators y'all have. I mean, obviously you can see, Jennifer, is my calculator sitting as yours? Okay, so we have, give me 1 second. So I have, like, Jennifer and I, our calculators are a little bit older. John's a little bit more advanced. I'm not sure how the Casio works. I don't have a lot of experience with Casio, but one thing I want to mention, and Steve, what kind is yours? Same thing? Okay. Matthias, what kind do you have? T84? Okay. So I'm pretty confident. I don't know. Yours, it doesn't have Inspire? It doesn't say Inspire anywhere on it? No? Okay. So I'm pretty sure all of us, and again, I'm not sure about the Casio, and I know John's works a little bit differently. John can just enter this in directly, and he'll get his answers. Our calculators, guys, you don't have a secant button, right? But aren't we aware that, and look, let me do this. Can I get rid of that too? 2 lows and 18, 9 times? No. This is, remember, this is, no, I'm sorry, this was seconds. That, I can see how it gets confusing, right? It was a unit of time, this was seconds. So I'll do that. I'll put SC so it's not, it doesn't look like the same thing. I see what you're saying here. Yeah. No, that was my bad. So give me 1 second real quick, Don. Look, this is going to give me a 9. So look, I can think of this as 9 pi. Remember, secant squared, y'all, is the same thing as 1 over cosine squared. So when we're doing this on our calculators, and again, I'm not sure how the Casio works, and I know, John's, you can just enter yours in nice like that, but this is how I'm going to have to do mine. So y'all, first thing I need to do, I need to make sure that I'm in degree mode, because the angle they gave me was degree mode, right? So look, we're going to scroll down over here. We're going to go to degree, okay? And again, if you have, whether you have an 83 or 84, just to give you a heads up, the way I'm doing this, hit mode, scroll down from radian, change it to degree, okay? And then go ahead and quit. And then we're going to enter in 9 pi. So I'm going to go 9 pi divided by, and I'm going to do in parentheses twice. So I'm going to do cosine of 20, close that off, and I'm squaring the whole thing. I don't know. Hold on. Give me 1 second. Let me go ahead and finish this off, right? So look, y'all, remember, because I'm having to square cosine of 20 degrees, right? So you could do it a couple of different ways. It's 9 pi divided by cosine of 20 squared. So you can say, what's cosine of 20? I don't know. Square it. It's that. And then take 9 pi and divide it by your answer. And still coming up with the same thing, right? Is that what we got earlier? No? Oh, it's 24 point something. What did I do wrong? Oh, is that what it is? I forgot to hit divide earlier. Okay. So yeah, 9 pi divided by parentheses cosine of 20. Okay, now square it. And there we go. There we go. Yeah, 32. 32 and change, right? So 32.0, I'd probably just go 02, right? If I'm going to say, if I'm going to go to 4 decimal places, it'd be 32.02. And this is feet per second. Okay. So again, the reason why I was doing it that way is because, again, our calculators, y'all, whether you have a TI 83, 84, 83 plus, they just don't have secant buttons. John's yours does though, right? You can do it. Does yours, can you just do secant directly, or you got to do the 1 over as well? You got to do the 1 divided by? Uh-huh. Okay. So if you have a newer calculator and Inspire, then you don't have to do the 1 over, but, you know, if you don't have it, you're just dividing it out, right? Because it's one of the properties of trig functions. We got to make sure that we divide that stuff out. Okay.
Well, you don't have to convert if you don't include the things to do. I just wanted to shoot my calculator in the middle, like
Convert it.
I convert it.
You can convert it.
Convert to three.
Yes. However one is. Yeah. Yes. Okay, so we got a couple more problems to do, y'all. I think we got about 3 more problems. Again, this is why I didn't want to do more than 4.1 today, because I know these problems are a little more heavy duty, right? They're all application based. And again, remember, the homework for this is not due until the Wednesday we come back. I would encourage you though to do some of it, right? Like, you know, work on the review, because that's obviously the more important part. I'm recording the lecture, so you're going to have all this stuff. You can always go back and rewatch parts that you need. But again, you know, don't let too much time pass. But I wanted to give you that time so that if you want to do it over the break, you know, you're more than welcome to, but you don't necessarily have to. Let's take a look here. It says at noon, ship A is 40 nautical miles due west of ship B. Ship A is sailing west at 18 knots and ship B is sailing north at 19 knots. How fast in knots is the distance between the ships changing at 5 o'clock? Note that 1 knot is the speed of 1 nautical mile an hour. Okay, let's draw a picture. Well, hold on, settle down. We'll figure it out in a second. Look. Okay, take a look. Here's ship A. Ship A, the distance between ship A and ship B right now is 40 nautical miles. Okay, ship A is traveling west at 18 knots, and ship B is traveling north at 19 knots. Okay, look, y'all, I'm going to call this entire distance here, I'm going to call that distance X. And I'm going to call this entire distance, I'm going to call that entire distance Y. Now, look what it's telling me. It's telling me the rate at which ship A is moving. That's telling me dx dt. So dx dt, it's going west. So it's going to the left at 18 knots. So that value is 18. Ship B is traveling north, and it's going at a rate of 19 knots. Okay. How fast in knots is the distance between the ships changing at 5 o'clock? Okay, so let me ask you a question. At different points in time, ship B is going to be doing this number, right? And at different points in time, ship A is going to be doing that number, right? It's moving to the left and it's moving up. So would you agree that the distances are changing as we go along? Okay, that's in essence what's happening, right? The rate of the distance is changing. Okay, so look, we're going to do this in pieces. Okay, we know that our time, right now we're at noon. Then we're going to figure out what happens at 5 o'clock. Would you agree with me that T has been 5 hours? Because from noon to 5 is 5 hours? Okay. What we want to do is we want to find some values here. Remember what X is. X tells me the complete distance on that axis right there, okay? We already know that this part of it is 40 miles, and then we're going another 18 knots, right? At 5 o'clock, I want to find the value of X. So I want to find the value of X at 5 o'clock in the afternoon. Okay, number one, we've already gone 40 miles, right? Because we already started off 40 miles that way. And then we're traveling at a rate of 18 knots, right? So isn't that going to be 18 times 5? Because each knot is the same thing as a nautical mile per hour, right? So I'm going to take my calculator over here, and I'm going to say, turn it on, I'm going to say, what's 40 plus 18 times 5? That's 9 but 5. So I'm coming up with 130, right? 130. So we know the value of X at 5 o'clock is 130. Okay, let's find the value of Y at 5 o'clock. So wouldn't this just be 19 times 5? $95? Okay. Y'all, let me ask you a question. Y'all agree that we got a right triangle here? That makes sense? Right triangle? If we know that this value is X and this value is Y, suppose we were to call that S, right? Just the distance between the two ships. Okay. So we said that Y at 5 was 95. Okay, y'all agree with me? According to the Pythagorean theorem, S squared is equal to X squared plus Y squared? Does that seem right? Okay. Let's plug in the values of X and Y that we know right now. Okay. Just for the distance for the ship. UZ. Okay. So the X value, didn't we get our X value 130? So 130 squared plus Y, which was 95 squared. Okay. So I'm taking my calculator again here, y'all. I'm just going to do some squaring. 130 squared plus 95 squared. 25,929. So I have the square root of 25,925. Sorry, I think I said 25,925. Okay, that's my value of X. What we're trying to find, though, I want you to look at the problem. The question says, how fast in knots is the distance between the ships changing at 5 p.m.? What we're looking for, y'all, we are looking for the SVT, because that distance has been changing. As time progresses, we said earlier, look, the distances were getting bigger and bigger and bigger, right? We're trying to find the rate of change at 5 p.m., okay? So, first thing we're going to do, we're going to use this equation again, okay? Just the general Pythagorean theorem. We're going to use this equation again. Remember how when we were finding the values of X and Y, I wrote them as functions of time because it depended on how much time had passed? So since we're trying to find dSdt, S is also going to be a function of the time, right? Like this is really going to be an S of t. That distance is represented, changes, right, based on the time. Do you understand why I'm putting it as S of t? Because as time changes, right, so does that value. So we're going to take the derivative on both sides, y'all, with respect to t. Okay. So look, we're going to do this one piece at a time. What's the derivative of s squared? I know you guys know that part. 2s. One extra factor though, right? Very good. ds over dt. Excellent.
Shouldn't we actually say the figure, 25?
Yes. Yeah, right here. Yeah. Yes, sir. There you go. You're right. Sorry about that. Okay. Same thing here. What's the derivative of x squared? 2x, one extra factor. Very good. dx over dt, right? Because it's the x. Okay, one more time. Jennifer, y squared. What's the derivative of y squared? You got this? Excellent. There you go. You got it. Perfect. I was picking on you because you were already on the right track, and I just wanted to keep you going with it. Okay, so I wasn't picking on you trying to be mean. I just wanted to keep going. But this is good, guys. We have these values. Okay. Okay. Question: is it okay if we get rid of those two? Because there's a two basically all the way throughout the equation, right? 0.956 gamma. Yeah. All right. I'm gonna assume that they're not taking any classes right now. Okay. All right. So anywho, we got rid of the twos. Okay. Next thing we're gonna do, y'all. We're trying to solve for ds dt. Is it okay if we divide everything here by s, just to get rid of the s's on both sides? We're getting rid of the s's, right? Okay. Now look, I know this part looks a little messy, but we're gonna clean it up right now. So look what we have on the left side. On the left side, y'all, we just have the ds dt. Okay, this step, y'all, is now plug and chug. Okay, this last step is going to be plug and chug. When we did our problem earlier over here, and we wrote out this whole piece, we came up with our x to be 130, and we came up with our y to be 95. We're going to start plugging those numbers in. Okay, so look, x we said was 130 times dx dt. Wasn't dx dt the same thing as 18? So I'm going to put an 18 right next to it. Plus y. Y we came up with was 95. And then, do y'all remember what dy dt was? Wasn't dy dt the same thing as 19? Right up here? So I'm going to put a 19 right here. Okay. All divided by s. Remember what s was? S was that big old square root of 25, 925. Okay. Okay, before I go on, are we good on how we got to where we are? I want to make sure that we're all okay on what we just did. So we got rid of the twos, we divided by s, and then the next step, y'all, was really just substitution. So now look, I'm going to take my calculator right here. We're going to go through one piece at a time. So I got 100, let me turn it on, figure it out. I got 130 times 18, plus I have a 95 times 19. I'm going to figure out what that is, and then we're going to divide it by the square root of, we had a 25,925. 925, there we go. And I'm coming up with about 25.734. And there's the rate at which the ships are changing, right? Now, do y'all agree with me that those ships were getting further and further and further apart? That's why that value was positive, because the ships were getting further and further and further apart. Therefore increasing. So therefore our DSBT ended up being a positive value. Does that make sense?
You think that accept it as just, non-rounded answer?
I don't know. You can try it. If it doesn't work, then put the rounded answer. Okay, so look, I'm gonna move. We got two more problems. I'm actually gonna do the street light problem last. Okay, I want to do this one next, and then we'll come back and do the street light problem. So this is the last. I scrolled down all the way to the last problem in the notes. There's two more problems left to do. I'm skipping the street light problem. We'll come back and do it in a second. I want to do this one first.
Sorry, so what was the unit something? No.
It would have been knots, right? Because knots nautical miles per hour. Yeah. Okay, so look, let me come back. Let's take a look at this one here. Same type of problem that we just did. That's why I want to do this one first. It says two cars are moving towards an intersection. Okay, so look, let's draw the picture. We got one car here, we got another car here. I'm going to call this car A. I'm going to call this car over here B. Okay, one car is 700 meters north of the intersection. Okay, y'all agree with me that this distance right here would be 170? And that is meters. Okay, so one car, I'm calling it car B. It's north of the intersection and is moving towards the intersection at a rate of 17 meters per second. So look, y'all, if I were to call the distance, because the distance is going to keep changing, if I call that distance y, wouldn't my dy dt be equal to a negative 17 meters per second? Why is it negative? Because we're getting closer to the intersection, right? So remember how before, y'all, we were measuring the distances? Aren't these distances now going to be getting like, they're going to be getting closer, right? Does that make sense? Okay, so that's why I really want us to understand. That's why I'm using like a negative value there, okay? Okay, now let's take a look at the next part. Let's see. Yeah, 170, because it says one car is 170 meters north of the intersection, going at a rate of 17 meters per second, while the other car is what, 190? And it's traveling west at the intersection at 20 meters per second. So if I call that distance x, wouldn't my dx dt be equal to a negative 20 meters per second? Does that make sense? Okay. Now the question says, how rapidly are the cars approaching each other 2 seconds later? So after 2 seconds, what we're trying to figure out is what is that value, the rate of change of the s, right? Okay, so remember what we said, y'all. My values of x and y are functions of time, right? So look, if I want to figure out what is x 2 seconds later, well, I knew the car was already 190 meters from the intersection. And then it is changing. The distance is getting shorter, right? So I'm going to subtract negative 20 meters per second times 2 seconds. So that's going to be 190 minus 40. So x at 2 seconds should be 150 meters. Okay. Now, let's find the distance y at 2 seconds. Well, we already know the car is 170 meters from the intersection. And because it's getting closer at a rate of 17 meters per second, we're going to find what the distance is after 2 seconds. So that's going to be 170 minus 34. So let me see, 170 minus 34, to 17 times 2 is 34, 136. Before I go on, are we okay in how we got to where we are? Yes. So remember what's happening, right? Here's car A. Right now it's at 190 meters from the intersection, right? But it's going in this direction. So what I want to figure out, Jennifer, is what is that value of x after 2 seconds? So he said, look, the car is already 190 meters away. It's traveling at a rate of 20 meters per second, but towards the intersection. So I'm taking 20 meters times 2, 140. And because it's going towards the intersection, now the car is 150 meters from the intersection. Does that make sense? And then I did exactly the same thing up here. I said, look, the car B was already 170 meters. It's traveling at a rate of 17 meters per second. So after 2 seconds, that car traveled 34 meters. So now the car is 136 meters from the intersection. Are we good? Excellent. Good. I want to make sure you guys are okay with this stuff. Okay, y'all, remember when we did the problem before, the first thing we did is we said, look, wasn't s squared equal to x squared plus y squared? And so what I want to do is I want to find the value of s at 2 seconds. So we're going to go ahead and plug our values in. So look, for x, we came up with a 150. So this is 150 squared. For y, we came up with a 136. So I got to square those numbers. 150 squared plus 136 squared. I'm coming up with 40,996. So s squared is 40,996, which tells me that s at 2 seconds is the square root of 40,996. Remember what that is. S is a function of the time, right? So the distance of those two cars 2 seconds later is now equal to the square root of 40,996, right? John, you got a question for me?
Yes. I was using some other application. So if you have a field where you have a where the field, you have to put field
Yeah, that's why I wrote it right here. S of 2. Okay. Look, y'all, just like we did before, we're going to take the same equation. S squared equals x squared plus y squared. Okay? And we're going to take the derivative of this function with respect to time. Okay. So just like we did earlier, what did we say the derivative of s squared was? Two s, one extra factor. There you go. Okay. Same thing over here. What's the derivative of x squared? 2x, very good. dx dt. Okay, excellent. One last time, the derivative of y squared would just be 2y dy dt, right? Okay, second thing, is it okay we get rid of our 2's? Okay, so look what we're going to have, y'all. We're going to have s ds dt equals x dx dt plus y dy dt. Okay. Last step, I'm going to divide both sides by s because I'm trying to find that ds dt. I'm going to divide everything here by s. So we now have ds over dt equals x times dx dt plus y dy dt all over x. Okay, so now I'm zooming out a whole lot because I want to see the values that I'm going to plug in. Okay, remember, we're finding that rate of change, right? So one thing I want to do right here, y'all, first part says, what is the value of x? Look at the value of x that we got earlier. You said x was what number? 150. The next part has a dx dt. Look right here. Here's my dx dt. Isn't that a negative 20? So negative 20 meters per second, okay? Plus y. Our y value, y'all, was right here. Wasn't it a 136? Times dy dt earlier when we did it, negative 17. Okay. Meters per second, you're right. Sorry, I forgot about that. Meters per second. Thank you very much, John. Okay. This next step, y'all, is just plug and chug, right? All right, let's see. Let me do this. Yeah, they're both meters per second, right? Okay, so look, let me clear this out. So I got 150 times, what, a negative 20? And a 136 and a negative 17. And all of that is being divided by the square root of 40,996. So on the top, I came up with a negative 5312. I don't know if you guys did. Anybody check on that? Make sure I got it. Yeah, I got the same thing? Okay. When we divide it out, y'all, look, I'm coming up with a negative 26.23, what, 54? If I go to 4 decimal places? So negative 26.2354. Negative 26.2354. This is meters per second. Okay, question. I want to ask you a question. Why was it negative? Because the rate of change in the cars was getting further away, or the cars were getting closer? They were getting closer, right? That's why that change all was negative. Okay. Again, I just want us to understand something. Why did we come up with a negative value? Well, yeah, we had negatives there, but why do we have negatives? Because the rate of change of those cars was getting closer to each other, right? So now look, I'm going to scroll back. I'm going to scroll back to my problem, right? And I'm going to take a look right here. And when you're doing this problem, y'all, this problem here, you have like a little menu, and you're going to click on that thing, and it's going to say, are the cars getting further apart, or are they getting closer? And you would obviously say they are getting closer, right? Just like when we did those first couple of problems earlier today, and it said at what value is the volume or the area decreasing, and because it already took the decreasing, since we're getting closer, we're going to enter in the positive value here, okay? And we came up with a 26 point something. And I think in the directions it said around the 3 decimal places, so I would just write 26.235. Okay, so right here, y'all, I would just write 26.235. And again, the reason I'm not putting the negative is because I'm saying the cars are getting closer. Does that make more sense? Okay, good. What do you mean? Yeah. Yeah, it doesn't do that. Yeah. Some of the newer ones do. This one doesn't. Okay, last problem here, y'all. The good thing we're only doing one section, right? Because these problems take some time to do. Okay, so let's take a look here. It says a street light is at the top of the 15-foot tall pole. A woman 6 foot tall lady, walks away from the pole with a speed of 6 feet per second along a straight path. How fast is the tip of her shadow moving when she's 40 feet away from the pole? Okay, so let's say we can figure something out here. Look, y'all, I'm gonna draw a little picture. We got a light pole. So here's my light. Here's the light. And then we have a woman, and how that woman is 6 feet tall. Okay, so here's the woman, and she is 6 feet tall, so the distance from here to here, 6 feet. We know that that light pole is 15 feet, okay? And let's see, what else do we know? Okay, we know the rate at which she's walking from the pole. Look, y'all, let's call the distance from where she's walking to the pole, let's call that distance x, okay? Do we not know a value for dx dt? X represents the distance she is from the pole. And it says she's walking away from the pole at a rate of what? 6 feet per second. So we know the dx dt is 6 feet per second. The rate at which this value is changing increases with respect to time, right? The question says, how fast is the tip of her shadow moving when she's 40 feet away from the pole? So look, y'all, if I were to think about this, this whole thing here as y, right? I can think of that whole thing there as y. How would I describe the distance from here to here? Anybody know? If the whole piece on the bottom is y, and from here to here is x, yeah, but hold on, I don't have circles or anything like that, right? My question is, how would I describe, say, that piece right there? No, you don't got to bring in another variable. Don't make it harder. Don't make it harder than it is. The whole thing on the bottom is y. This first part is x. Wouldn't this just be? Does that make sense? Right? It's the whole thing minus the other little piece. Okay. Question: do we have similar triangles here? Do we got two triangles that look alike? Like a big triangle and a little triangle. Look, here's the big triangle, right? Boom, there's the big one, right? I'm drawing it outside so you can kind of see what I'm doing. Here's the little one. Okay. Remember, when we have similar triangles, y'all, we can write proportions. So let's compare the big triangle to the small triangle. The big triangle, the height of the big triangle is 15. The base of the big triangle is y. Okay. The height of the smaller triangle, how tall is the smaller triangle? 6 feet. The base of it, what are we calling it? Y what? Y minus x. Does that make sense? Okay. So what we're going to do here, y'all, we're going to do a little cross multiplying. Y times 6, 6y. 15 times y minus x, everybody agrees that 15y minus a 15x. Does that make sense so far? I'm distributing the 15 to both pieces. Okay? What I want to do here, y'all, I want to solve for y. Okay? You agree minus 15y on both sides? So those will go away. 6 minus 15 is a negative 9y equals a negative 15x. If I wanted to solve for y, how would I get rid of the negative 9? Divide everything here by negative 9. Okay. So first thing, a negative over a negative is a positive. Can we reduce 15 and 9 at all? By 3. So 5 over 3 with an x. Okay. All we did, y'all, is just set up a proportion. Okay. We set up a proportion. We had two similar triangles. We set up the proportion. I want us to think about what the question is asking me to do. The question is saying, how fast is the tip of her shadow moving when she's 40 feet away from the pole? We're trying to figure out at what rate is that value changing, right? Okay, that value, y'all, is represented by y. It's the whole thing on the bottom, okay? It's the whole thing on the bottom. What we're trying to do, y'all, is we're going to take the derivative on both sides with respect to t. Okay? So the derivative of y with respect to t, y'all, is just that dy dt. Right? The derivative of y would be 1, but I got to use the chain rule, so I got to do the dy dt. 5/3, the derivative of x, isn't that just dx dt? Okay. So now dy dt equals 5/3 times, didn't we have a value for dx dt when we first got started? Dx dt was how much? Right up here. Remember, dx, it was 6 feet per second because it said that's the rate at which that value right there is changing. So that's 6 feet per second. And now all we got to do is a little simplifying. That goes in twice. So 5 times 2. The rate at which her shadow, the tip of her shadow is moving is 10 feet per second. And we're done. Okay, so let me go ahead and stop recording here.